This is the second and last video in a series in which we try to find the shapes of simple molecules based on the Lewis dot structures, and then the number of electron groups around a central atom and the number of lone pairs in those electron groups. In the prior video we have seen how those combinations emerge for 2, 3 or 4 electron groups and a varying number of lone pairs. In this video we concentrate on the a little bit more complex situations where you have 5 electron groups and 6 electron groups and varying numbers of lone pairs. Right, so let's go to 5 electron groups. We know from VSEPR theory that the geometry that minimizes repulsion when you have 5 electron groups is what we call a trigonal bipyramid. Okay, so this is the shape of a trigonal bipyramid, and something that is important about a trigonal bipyramid is that there's 2 different locations, right? Notice that this location, which we have right here, right, so that's a location, and this location around the central atom, those are different from the locations that you have in this plane. Okay, this is actually what we call axial locations, and these are what we call equatorial locations. All right, so the angle between these electron groups will be 180, and the angle between these electron groups is 120. Okay, and any angle between the axial and the equatorial locations will be 90 degrees. Okay, all right, so if you have a molecule in which the 5 electron groups happen to be bonds, then the shape around the central atom is what we call a trigonal bipyramid. Okay, so we come to the table and write trig bipyramid for short. Where an example here is given by phosphorus pentachloride. Okay? Right, great. And then now we try to see what happens when some of those bonds actually are not bonds but happen to be lone pairs. Okay? And this is going to be a very interesting discussion because you have 2 different possibilities. Right? Notice that there's 2 different locations, axial and equatorial. So then we have to ask the question of where does the lone pair go? Does it prefer an axial position or does it prefer an equatorial position? Right, so we can actually see how that would work by just playing with the 2 possibilities, right? So suppose that I remove one of these bonds from an axial position and replace it with a lone pair. All right, what we will have right here is that this lone pair is now close to 3 bonds, right? So notice that that lone pair is on average about 90 degrees from that bond, from that bond, and from that bond. Now, something that is very important is that lone pairs exert more repulsion than bonds. Okay, so what you would like to do is place the lone pair in the location where electron repulsion is minimum. Okay, so if we replace the axial, if we place the lone pair in the axial position, we're going to have repulsions with these bonds, with 3 of these bonds at 90 degrees. All right, so now we're going to compare that situation with replacing one of the bonds in the equatorial sides as opposed to in the axial sides, and we will remember that again, when you place the lone pair in the axial side, what happens is you have 3 bonds at 90 degrees. Okay, all right, so let's recover here the trigonal bipyramid, and instead of removing one of the lone pairs from the axial position, we actually now are going to remove it from the equatorial position, which will be this one. Right, and try to place here the lone pair. Okay, so that will be a bond from the equatorial position gone, and then we'll replace that with a lone pair. And again, we know that this lone pair exerts more repulsion than a regular bond. Okay, so now we're going to see how many groups you have close by and compare that to the other situation, right? So when we put the lone pair in an equatorial position, we have that there's 2 bonds at 90 degrees, right? So notice that this is significantly different from the lone pair in the axial position where we had 3 bonds at 90 degrees, right? So it turns out that this actually has lower repulsion than the other situation. So this is actually the preferred shape. Okay, so when you go from a trigonal bipyramid and replace one of the bonds with a lone pair, the location of the lone pair that minimizes repulsion would be an equatorial location, and that means that now if we examine what the shape of the molecule would be, this is what we call a seesaw. Okay, that is the shape that remains in the molecule. Okay, so again, going back to our table, we can say that the shape for when you have 5 electron groups, but one of them happens to be a lone pair, that is what we call a seesaw. Okay, and an example for a seesaw would be SF4, sulfur tetrafluoride. And again, I encourage you to draw the Lewis dot structure and verify that SF4 really corresponds to 5 electron pairs, where one of them should be a lone pair. All right, so this is our seesaw, and we can continue to ask questions about, well, what happens if now we remove another bond, right? What type of shape would you expect to find? Well, and as the situation is much as what we had before, right? Notice that there's still 2 different locations from which I can remove the bond and place a lone pair, right? I could remove this bond and put the lone pair right here. That will be an axial position. Or I can remove this bond and place the lone pair right here, and that will be an equatorial position. The question is which one of them, which one of those 2 possibilities minimizes electron repulsion, right? So I'm going to start first with the axial position right here. I'm going to remove this and now place the lone pairs. All right, so let me get the lone pairs. This will be the situation, right, where have these lone pairs right here. Okay, and something that is important is that those lone pairs are actually now 90 degrees from each other. Okay, so that will be a situation that elicits a lot of electronic repulsion. Okay, again, so we should remember this when we have the combination of 2 lone pairs in this trigonal bipyramid. If we go from a seesaw and remove one of the axial bonds and replace it by a lone pair, now I have 2 lone pairs at 90 degrees from each other, which again is going to elicit a lot of repulsion. Now let's try to see what happens if I place the second lone pair in the other position, right? So again, instead of removing it from an axial position or placing it in an axial position, we actually are going to now remove this from an equatorial position, right? So you will have that there's now 1 lone pair right here, and the other lone pair would go into this location right here. And notice now the angle between the lone pairs, which I'm going to try to get back here. Okay, that bond between these lone pairs is not 90 degrees as it was in the other situation, but is now 120 degrees. So it's very clear that the preferred location of the lone pairs is actually both in equatorial positions, and the resulting structure from placing those lone pairs in equatorial position is what we call a T-shaped molecule. Okay, so we go to our table, and then place here what the shape is going to be for 5 groups of electrons, where 2 are lone pairs. We know that the situation that minimizes electron repulsion is the 2 lone pairs in equatorial positions, and this is what we call a T-shape resulting molecule. Okay, T-shaped. T-shaped. All right, so an example for a T-shaped molecule, for example, will be ClF3. And as always, I encourage you to go do the Lewis dot structure for that ClF3 molecule, chlorine trifluoride, and verify that you will get a 5 electron groups and then a T-shaped molecule. All right, so the last possibility here would be to remove one of these other bonds, right, and see which one minimizes repulsion, and then the situation here is very simple. Okay, we will have that you either remove one of these, right, or that one. Okay, notice that if you remove one of these, now you're going to have more electron repulsion than if you remove the other one, right? So the situation here would be once you go to 3 electron groups, okay, 3 lone pairs in trigonal bipyramid. Again, notice that it's always less repulsion to remove the bonds that are in equatorial sites and replace them by lone pairs. Okay, so the resulting shape that you would get out of this would be linear. Okay, so for a molecule with 5 electron groups in which 3 of them are lone pairs, okay, the original shape would be trigonal bipyramid, and then all the lone pairs go to the 3 equatorial positions, and that means that the resulting shape of the molecule around the central atom is linear. Okay, so this will end up being linear, and a molecule that has the shape will be the triiodide molecule, okay, with a minus sign. Di. Okay, great. So we're done with the possible shapes for molecules that have 5 electron groups around a central atom, and we're just left with the last case in which you can have 6 electron groups around a central atom. Okay, so let's see if we can go through those. Okay, that will be the original shape. Okay, this is a central atom that has 6 electron groups, and if those 6 electron groups happen to be atoms or bonds to atoms, then we know that the shape of that molecule around that central atom will be octahedral. Okay, so that is the original shape, no lone pairs. This is what we call an octahedron. And the archetypal octahedral molecule will be sulfur hexafluoride. Okay, so much as before, what we're going to do is continue to, or begin to replace some of these bonds with lone pairs and see what the shape should be. All right, so in this case, there's actually no 2 types of positions. You don't have equatorial and axial. All of the positions are exactly the same, so it doesn't. There's no discussion here, right? You remove one, the one that you prefer, and then examine what is left over. Okay, so we'll replace that bond with a lone pair, and then see what the shape of this molecule will be. Okay, yes, to ease the visualization, we're going to remove the lone pair. Notice that the shape that remains is what we called square pyramid. Notice that you have a square base and then a pyramid. Okay, so that molecule, that shape around the central atom is what we call square pyramidal. All right, so the shape here will be square pyramid. And a molecule that follows this shape would be bromine pentafluoride. Okay, and you can see that from drawing the Lewis dot structure. All right, and then we're done to the last possible shape that is known. Okay, now you remove a second bond from this situation in order to be able to see what the shape, the resulting shape should be. Right, so we have here a lone pair, and we're going to remove one of the other 5 bonds to place a lone pair. And the question that we're asking ourselves is, well, what would be the location of that lone pair that minimizes repulsion? Right, notice that if I remove any of these 4 atoms right here, or these bonds, and replace it with a lone pair, then what I will be doing is putting a lone pair 90 degrees from the existing lone pair, and that will elicit a lot of repulsion. However, if I remove this bond that is opposite to the lone pair, then the angle between those 2 lone pairs would actually be 180 degrees, and that would result in much less repulsion. So that is actually the preferred shape, okay, where you just have the original octahedral shape, but now you're replacing 2 of the bonds with 2 lone pairs, right? So if we drop the lone pairs, then the resulting shape that you have of the molecule is what we called square planar. Okay, so for 6 electron groups and 2 of them are lone pairs, we have that the shape is square planar. And a molecule that has this shape will be xenon tetrafluoride. All right, so in the last couple of videos, we have gone through all simple possibilities of number of electron groups around a central atom, and then the shapes that ensue according to whether all those electron groups are bonds or some of those electron groups are lone pairs. Okay, so we have here a beautiful mosaic of possible common structures that we find in nature. And again, I guess the important thing about this is that you need to know how to draw Lewis dot structures and then use electron repulsion arguments to be able to see how these shapes emerge. And again, the overall idea here is that when you have lone pairs, you gotta try to put those lone pairs in situations that minimize repulsion.